The next section we're taking a look at is section 3.9. 3.8 is all about exponential growth and decay. Fabulous topic, great application of calculus, but there isn't a whole lot of new stuff there. There's a review of some of the algebra of exponential functions and a review of some of the calculus of exponential functions. And just in the interests of time, I wanted to make sure that we had time to really dedicate ourselves to the new stuff that we're doing. So 3.9 is about related rates. And the two key concepts that we need here are that things that change are functions of time. If something changes, it has one value now. Time passes, it has a different value at a different time. So I can think of time as the input and the value of that changing thing as the output of that function. Okay. And then the second key concept is if I have a relationship between two or more functions, that's going to induce a relationship between their rates of change. So that if they're differentiable functions, that induces a relationship between their derivatives. So here's the example I want to take a look at. We're going to suppose that the pandemic is over and that we're actually allowed to go to this physical place called school. Okay. And we've got two friends. This is going to be Maude's house over here, so I'll draw in Maude. She's so happy that she can go to school. Okay, she's as big as her house too. So this is Maude's house. Now, Maude happens to live due east of school, and she lives a total of 9 miles east of school. Okay. Now, her good friend Harold happens to live due north of school. Harold is also as tall as his house, so this is Harold's house here. And he lives due north of school a total of 4 miles. And so one day, Harold calls up Maude and he says, "Maude, would you like to meet me at school so we can study calculus together?" And Maude jumps for joy and says, "Oh, Harold, there is nothing in the world I like better than meeting you at school to study calculus. I shall head to school right now." And at the very same moment, they both begin walking towards school. So Harold's going to walk this way, and he's walking at 2 miles per hour. Okay. And Maude's going to walk this way, and she's walking a little bit faster. She's going at we'll let her go at 4 miles an hour. Harold's kind of dawdling just a little bit, but that's okay. He has a shorter distance to go. Okay, so the question I want to answer is, after 1 hour, how fast is the distance between Harold and Maude changing? Okay, excellent. So let me clear some space here. I'm going to just notice that at every moment in time, we're going to have a right triangle like so, where here we've got the school, here we've got Maude, and here we've got Harold. So I'm going to just label M is going to be Maude's distance from school. Now, that's not the same as how far Maude has walked, because Maude's house might be over here. This would be how far Maude had walked, but that's not in this triangle. The distance that Maude still has to go to school is what I'm calling M. Okay. Same thing with Harold. I'm going to let H be Harold's distance from school. And that's not necessarily the same as the distance that he's walked, because his house might be further up there. Okay. And I'm going to let D represent the distance between Harold and Maude. Okay. And let's see, what I know is that Harold was walking at 2 miles per hour, and the initial distance was 4. And Maude's walking at 4 miles per hour, and her initial distance was 9. Okay, so what I'm going to do is, this is sort of the active picture. This is what I have at every moment in time. We are asked what happens after 1 hour. So I'm going to draw the static picture, just taking a snapshot in time. After 1 hour, what we're going to have is, if Maude's walking at 4 miles an hour and she started with 9 miles to go, she'll have walked 4 of those. M is going to be 5 at that time. Okay. Harold had 4 miles to go. He was walking at 2 miles an hour, so he's gone halfway. He's got 2 more miles to go. And I could actually figure out the distance, but we'll do that in a bit. Okay. So H, M, and D are all changing. Harold and Maude are both getting closer to school, and as they get closer to school, they're getting closer to each other as well. Okay? And since these distances always make up a right triangle, I know that they satisfy the Pythagorean theorem. So m squared plus h squared is equal to d squared. That's my relationship between 3 functions of time. Now, each of these pieces then is a function composition. This is a function of time plugged into the squaring function. This is another function of time plugged into the squaring function. And this is another function of time plugged into the squaring function. So, since this is all about how a relationship between the functions induces a relationship between their derivatives, let's take the derivative of both sides. So the derivative with respect to time of m squared plus h squared will equal the derivative with respect to time of d squared. So we're just using implicit differentiation. We have here 3 different functions of time, but anytime I'm taking the derivative with respect to t of something other than t, that's going to be an implicit differentiation. So the derivative of the squaring function, I just double my input, so I'm going to get 2m, and then times m prime. Plus, same thing here, derivative of the squaring function, now I get 2h, and the derivative of the inside part is h prime. And that's going to equal, same thing here, derivative of the squaring function, this time is 2d, and the derivative of the inside part is d prime. Okay. So you'll notice the relationship between the derivatives does take into account also the original functions, and that will often be the case because the value of the derivative varies depending on the point at which we're evaluating it. Okay, I think just to simplify this, I'm going to divide through by 2, get rid of that 2, and we've just got m prime plus h prime equals d prime. Now d prime is what I want to know. I was asked how fast the distance between Harold and Maude is changing at this moment in time. So what that means is I need to plug in for everything else. Okay. So we're 1 hour later. We've already calculated what m and h are. So m is Maude's distance from school. That was 5. Now m prime. Take a moment. See if you know what m prime is. I'm guessing a lot of you said 4 because Maude is walking at 4 miles an hour. But m prime is -4. Okay. Have to be very careful with these problems. We're going to be given verbally the value of certain derivatives. And that's almost always going to be the absolute value of the derivative. Because in math, when something is decreasing, we indicate that with a negative sign. In English, when Maude's distance to school is decreasing, we communicate that by saying she's walking to school. Okay? So that would mean that her distance from home is increasing, but her distance to school is decreasing. So these are word problems. They're going to be given to you in English. So you'll be told how fast something is changing, and you'll be told indirectly often the direction in which it's changing. You need to interpret that and translate that into the math way of saying whether something is increasing or decreasing. Her distance to school is decreasing, so m prime is -4. Okay. Plus h. We said Harold's distance at this moment in time is 2. H prime. Now Harold's walking at 2 miles an hour, and just like with Maude, his distance to school is decreasing. So that's going to become a -2. And that's got to equal d times d prime. So I need to know d at this moment in time. Well, that's this right here. And for that, I can use this original relationship between m, h, and d. That's the right triangle I have at this particular moment in time. So I know that d squared is 25 plus 4. That's 29. D is a distance, so it's positive, so it's the positive square root of 29. So now I can solve for d prime. Okay. So this is going to be -20 minus 4 equals root 29 d prime. D prime, that's just going to be -24 over root 29. Okay. Now, that's the math answer. I always want to answer the question. If it was asked in words, I want to answer it in words. And I'm going to want to include the units in my answer, because we're always talking about rates of change. Nice to have the units. Okay. So I'm going to say the distance between them is decreasing at a rate of 24 over root 29 miles per hour. Now, what happened to the negative sign? It became the word decreasing. Okay. And in general, the way we talk about rates in English is we give the absolute value of things and we use words to indicate the direction. So almost always the answer in words is going to involve the absolute value of the derivative. And so here, the derivative was negative. That told us it was decreasing. But the answer to the question is the distance between them is changing or decreasing at this rate. Even if I just use the word changing, we don't talk in just plain English and say it's changing at a negative rate. We would just say it's changing at this rate. Oh, and by the way, it's getting smaller. We use words to indicate the direction. Okay. Now, that doesn't mean you could just forget these negative signs and get this. In this particular case, every derivative involved was negative. So if you left out the negative sign, you would get the right answer. You would not, of course, get full credit. I want to see the correct math answer and then the correct answer in English. Okay. But there are going to be plenty of times where some of the derivatives are positive and some of them are negative. And then if you leave off the signs and make them all positive, you're going to get the wrong answer. Okay. All right. As for the units, it was miles per hour. If I write that as a fraction, notice we were looking at d prime. It's just the units for d divided by the units for time. So d was a distance. All of these distances we were measuring in miles, and all of the times were given in hours because our other rates were miles per hour. And we were told this is the time 1 hour after we'd started. Okay. So you do need to sometimes check. In this case, all of the rates were rates of change of distance, so they all had the same units. But sometimes you're going to have related rates of different quantities. You might have something like a length and an area. So if the length was in inches, the units for area would be square inches.